Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. We hope you are all doing well. Have you ever wondered how your body turns fat into energy? It's not magic, it's biochemistry. In this presentation, we'll explore fatty acid beta oxidation, the energy pathway from fat, a fascinating metabolic journey that transforms fat into the fuel your cells need to function. Before we begin, allow us to introduce ourselves. My name is Vika Putri, student ID 240107510009. And my friend Mardatila with student ID 240107510005. Seven, and we're excited to guide you through this essential metabolic pathway. So let's dive in and explore how our bodies turn fat into fuel.
Fatty acid beta oxidation is a catabolic process in which fatty acids are broken down within the mitochondria into acetyl coenzyme A through a series of repetitive reactions. The name beta oxidation comes from the position of the carbon being oxidized, namely the beta carbon, third carbon from the carboxylate end. Each beta oxidation cycle cuts two carbon atoms from the fatty acid chain and produces one molecule of acetyl coenzyme A, one molecule of nicotinamide adenine dinucleotide, and one molecule of flavin adenine dinucleotide. Acetyl coenzyme A then goes into the citric acid cycle, while nicotinamide adenine dinucleotide and flavin adenine dinucleotide are used to produce ATP via the electron transport chain. This process repeats until the entire fatty acid chain is completely broken down into acetyl coenzyme A units. Long-chain fatty acids that have been activated into acyl coenzyme A cannot directly cross the mitochondrial inner membrane. Therefore, the body uses a specialized transport system involving carnitines to carry these molecules into the mitochondrial matrix, where beta oxidation takes place. This process consists of three main stages. First, activation of fatty acids in cytosol. Second, fatty acid transport into mitochondria. And third, beta oxidation in the mitochondrial matrix. 1. Activation of fatty acids in cytosol. Before fatty acids can be broken down, they must first be activated. This happens in the cytosol, where free fatty acids are converted into acyl coenzyme A. The enzyme responsible for this acyl coenzyme A synthetase. The reaction is as follows: fatty acid plus coenzyme A plus ATP can produce acyl coenzyme A plus AMP plus pyrophosphate or PPI. This step requires energy from ATP and takes place on the outer mitochondrial membrane facing the cytosol.
Second, fatty acid transports into mitochondria. Now that we have acyl coenzyme A, we need to get it into the mitochondrial matrix where beta oxidation takes place. But there's a problem. Acyl coenzyme A cannot pass through the inner mitochondrial membrane by itself. So the body uses a shuttle system called the carnitine shuttle. First, acyl coenzyme A is converted into acylcarnitine by the enzyme carnitine palmitoyltransferase 1. Then, carnitine translocase helps transport the acylcarnitine across the membrane. Finally, inside the matrix, carnitine palmitoyltransferase 2 converts acylcarnitine back into acyl coenzyme A, now ready for oxidation. Third, beta oxidation in the mitochondrial matrix. Now we get to the heart of the process, beta oxidation inside mitochondrial matrix. This process involves four enzyme catalyzed states, which are repeated in cycles. The four states are dehydrogenation, hydration, oxidation, and thiolysis. Let's go through each one in detail. First, dehydrogenation. The first step of beta oxidation involves the oxidation of fatty acyl coenzyme A by the enzyme acyl coenzyme A dehydrogenase. which is a double bond between the alpha C2 and beta C2 carbons of the molecule, forming trans delta 2 enoyl coenzyme A. Second, hydration. Next, a water molecule is added to the trans double bond in a reaction catalyzed by enoyl coenzyme A hydratase. This state forms hydroxyl group on the beta carbon, a compound known as 3-hydroxyacyl coenzyme A.
3. Oxidation. The hydroxyl group is then oxidized to a keto group to form beta-ketoacyl coenzyme A by 3-hydroxyacyl coenzyme A dehydrogenase, restoring the trans double bond and generating a nicotinamide adenine dinucleotide. 4. Thiolysis. The final step involves cleaving the terminal acetyl coenzyme A group beta-ketoacyl coenzyme A by thiolysis, releasing fatty acyl coenzyme A with a fatty acid chain shortened by 2 carbons. The enzyme thiolase catalyzes this reaction. The overall equation of one cycle of beta oxidation is acyl coenzyme A plus flavin adenine dinucleotide plus nicotinamide adenine dinucleotide plus hydrogen plus coenzyme A can produce acyl coenzyme A plus flavin adenine dinucleotide plus nicotinamide adenine dinucleotide plus hydrogen ion plus acetyl coenzyme A. This system ensures that only activated fatty acids can enter the mitochondria and undergo beta oxidation. This transport is also an important regulatory step to control when and how much fatty acids are oxidized to produce energy.
Now, let's take a closer look at the products generated through the process of beta oxidation. The main products of each beta oxidation cycle are acetyl coenzyme A, FADH2, NADH, and proton H+. What happens to these products depends on the energy needs of the organism. For example, acetyl coenzyme A may enter the citric acid cycle to produce a more ATP, or be used as a building block for synthesizing other molecules, such as fatty acids, depending on cellular context. The amount of ATP generated depends on the size of the fatty acid being oxidized. Let's take palmitic acid as an example, a saturated fatty acid with 16 carbon atoms. When completely oxidized, palmitic acid undergoes 7 rounds of beta oxidation, producing 8 molecules of acetyl coenzyme A, 7 molecules of FADH2, and 7 molecules of NADH. Each acetyl coenzyme A yields about 12 ATP through the citric acid cycle, giving us 96 ATP. Each FADH2 produces about 2 ATP, so 7 FADH2 gives 14 ATP. Each NADH produces about 3 ATP, so 7 NADH results in 21 ATP. In total, that's 96 plus 14 plus 21 is 131 ATP. However, we subtract 2 ATP used during the initial activation of the fatty acid, giving us a net yield of 129 ATP from one molecule of palmitic acid. In terms of energy, this is equivalent to about 23 and 40 kilocalories. The overall chemical reaction for the complete oxidation of palmitic acid is 1 molecule of palmitic acid reacts with 23 molecules of oxygen to produce 16 molecules of carbon dioxide, 16 molecules of water, and release 2,340 kilocalories of energy. This clearly shows how efficient fat is as a long-term energy storage molecule. And that's the end of our presentation. To summarize, the fatty acid beta oxidation is a powerful metabolic process that breaks down fat into energy. It involves activation in the cytosol, transport into mitochondria, and a four-step oxidation cycle. We hope this presentation helped you understand the pathway from fat to fuel more clearly. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.